All right, good morning, everyone. We're going to talk about a lot of recent developments in Ethernet, and it kind of ties into some of the tutorials and other talks that we've had here. So it's almost like we planned it this way. I found this diagram, which I really like, that Bob Metcalf drew in 1972, and so now it's about 28 years later, and it turns out that he was kind of right. So we do see Ethernet almost everywhere, from the last mile into wireless and obviously data center and networks like that. So basically this is going to be a whirlwind talk. We have 58 slides and 28 minutes, or 25 minutes, but it's okay. We've done this before and no one died. But basically I'm just going to give you an overview of all the stuff that's going on with some references, and then you can read about the stuff that's interesting to you in your spare time. But there is actually a lot of stuff going on. We have 40 and 100 gig Ethernet that is now, the standard is now done. We have IEEE, which is energy efficient Ethernet. We have a lot of carrier Ethernet and OAM tools that are now available. Then we have the whole data center bridging and shortest path forwarding for layer 2 networks. So we're kind of talk about all those in brief and go kind of quickly. First, I wanted to start out with the slides for all the standards organizations, because I go to a lot of these meetings and I talk to all these people and I know all these organizations. So I kind of try to draw this as an OSI model where the bottom is sort of the physical layer. So that's the components and interface standards. That's called the OAF. And then as you move sort of up the stack, you have the fiber channel, you have the IEEE, which makes the Ethernet standards, then you have the ITU, which makes the telecom standards. Then you move up higher in the stack and you get the IETF, and then the Metro Ethernet Forum, and then at the very top are you and your customers. So the thing that I want to point out is that as you move higher and higher up the stack of standards organizations, we see more involvement by service providers and internet exchanges. So in the Metro Ethernet Forum in particular, where they're working on service definitions and standards for Ethernet services, we see a lot of service providers and now a lot of internet exchanges involved because of the carrier Ethernet exchanges that people like Equinix and Telex are doing. So you can kind of refer back to this slide as I throw out the standards acronyms. Now let's talk about 40 and 100 gig Ethernet first. So we're done. I've been talking about this for about 5 years, so I'm very excited that we actually are almost to the state of shipping product. The standard was pretty much done this spring, and we had to go through some formalities. It was approved in June, and it's a whopping 457 pages long, so it's a massive set of standards for both 40 and 100 gig Ethernet. This are the sort of the target applications, and just because I say target applications doesn't mean that someone won't use the technology, in other places. We always find interesting ways to be creative when we design our networks, but this is basically where we think that it'll be used. 40 and 100 gig. 40 gig is basically targeted towards data center applications, so maybe a data center core, especially towards top of rack and blade server access. As the servers get faster and the PCI bus increases, we think that they'll need 40 gig sometime in the next couple of years. Also maybe for a small campus core or something like that. 100 gig on the other hand, it's really targeted for large service provider networks or large data center aggregation, large campus cores and things like that. Here's a slide that I keep updating, and it gets denser and denser and harder to read, so I hope you can see it in the back. The thing that I want to point out here is that I added a price row. So this stuff, it turns out it's a little bit more expensive than we thought it would be, especially as we get into longer reach 100 gig optics. It's just very insanely expensive, and I'll talk about that a little bit more. But this is basically the physical specifications and the type of media that we'll be using for 40 and 100 gig. So second generation technology, even though I said the standard was just approved in June, we're already starting to work on new things, and that's good because we want new technology to evolve as it becomes feasible. So the standard is really flexible, just like 10 gig where we had CX4 and 10G base T and all this stuff evolve over time. The same thing will happen with 40 and 100 gig. So there's already a new project in the IEEE to do a 40 gig serial for 2 kilometer, and then we also expect that there will be 2 new call for interest later this year to do a shorter reach copper cable and a backplane Ethernet that uses 25 gig signaling, possibly a low cost 2 kilometer module that would use 4x25 signaling, and then a new optic called QSFP2, which is still being defined. The other thing that's going on is because the standards-based optics are so insanely expensive, and I mean the list prices of several tens of thousands of dollars, there's a very strong interest in the operator community to support a non-standard low-cost optic that uses 10 by 10 signaling that would go up to 2 to 4 kilometers. So I think that'll be something that we're going to investigate, and that could possibly come out as a multi-source agreement that would be a non-standard from the IEEE. So interesting developments there. As far as what's going on beyond, right now what's keeping us from making cheaper interfaces is the fact that inside the box for chip-to-chip communications, we basically have 3, 6, or 10 gig SerDes and components that we can use inside the box. What we really need is faster signaling inside the box to get rid of all this 10 by 10 conversion that we're doing and 10 by 10 aggregation on electrical interfaces. So the OAF, that's the standards organization that does semiconductors, is working on some really fundamental 25 gig signaling that's going to change the way that we do things. So when we have that kind of signaling, we'll see a couple new projects in the IEEE that will use a true 4 by 25 gig interface from electrical to optical. Right now we have a 10 by 10 electrical that gets converted into a 4 by 25 optical, which adds a lot of costs and components. And then as far as what's going beyond, we'd like to do terabit Ethernet, but it's really not possible right now as far as technology and economics. I mean, we could build it, but people are already having a hard time affording 100 gig Ethernet, and terabit Ethernet would be pretty much unfeasible. 400 gig Ethernet could be a choice in, say, mid-2000s, 2015, by using 16 by 25 gig signaling, but that's just an idea that's really being kicked around right now by network operators, and I think we'll see some more evolution in the next couple years. But it's clear that as far as Ethernet, there's a lot of demand for it in different form factors, and eventually I think we'll see a true serial 100 gig, though it may not be a couple years just because of our technology. All right, what should you expect this year? There's lots of announcements. 4 companies have started to announce and or ship 100 gig interfaces, and there's one company that's doing 40 gig, so I just want to leave it at that as far as where we see the technology going. And like I said, it's kind of expensive, so here's a chart that I drew based on the historical prices of 10 and 1 gig Ethernet, and you can see that in the first couple years the price has dropped by almost half or over half in some cases. So we think that the same thing is going to happen with 40 and 100 gig based on the historical pricing. Like I said, the optics are really what's the most expensive right now because there's no volume. I mean, the optics manufacturers are practically making them by hand, and we may sell, we meaning the industry, may sell 100 of these interfaces this year or next year. So when you have that kind of low volume, there's just no cost benefit in volume production. And then second generation technology, like I said, will allow us to do denser interfaces and lower the prices too. Here's some references, and I'll just kind of skip over these. All right, so energy efficient Ethernet. This is, I think, a really interesting new technology that probably hasn't gotten a whole lot of press or interest in the operator community. I think it's interesting, though, because of the power consumption. So what it does basically is introduces a mechanism that will reduce power consumption on the link during periods when it's not used. And you can see this, or I hope you can see this chart from Intel, and you notice that an idle and a line rate interface really uses about the same power. But if you run an interface at, say, 10 meg versus 1 gig, you actually save a lot of power. So the idea is, just like your CPU scales back when it's kind of idle, is that we're going to scale back the speed of the network interface to transmit at the most energy efficient speed possible. So the standard was just approved last week, and I think it'll take a while, because this has to go actually into the silicon. I think it'll take it a while before we see products, but I'd estimate that we see something in probably 2011 or maybe even sooner. So the way that this works, like I said, is if you're transmitting, say, a couple megabytes, then you run the link at 10 meg. If you're transmitting a couple 100 megabytes, you run the link at 100 meg. And if you're going beyond that, then you run the link at a gig. Also, there's times when you're actually not transmitting anything. So like on a voice over IP connection, for example, you may only transmit something once every 10 or 20 milliseconds. So you can actually idle the link for several milliseconds when there's no traffic to send. So there's two things, is the speed selection and then the low power idle. And this is basically how it works. Everything looks like normal. Obviously we can't flap the link and things like that. So the link is always up. No frames are dropped or corrupted, obviously, and then the time has to be transparent. So we're talking about millisecond transition times between 10 and 100 or even gig speeds, just like your CPU does, like I said. And this is the interesting thing, is because if you're already turning off the network interface, then there's also other components in servers that you could turn off. So for example, you could turn off CPU cores because you know your network interface is off and there's nothing to send or receive, so you might as well turn off your CPU. You could, I don't know, turn down some memory so that you don't have to keep refreshing it or things like that. So I think this will lead to other areas in server design that will lead to a lot more efficient utilization. And then the way that this is done is with LLDP extensions and auto negotiation. So obviously there's mechanisms to set servers at a particular speed, or there will be, because some servers you may never want to do this negotiation. So I think this is really interesting. There's a good tutorial on the IEEE webpage that talks about some of the background and some of the power efficiencies and savings that we think we can get. But you know, if you imagine that large companies have several 100,000 servers, and if we start doing this around the world, that could be significant energy savings. Okay, Ethernet ring protection switching. This is a new standards-based protocol for Ethernet rings. We've had a number of vendors. I think everyone probably has their own proprietary ring technology, but this is finally a usable standards-based protocol for rings. The good thing about it is, unlike IEEE, which we just talked about, this is a protocol. So there's no need for any hardware changes or anything like that. So it's relatively easy to implement. The first standard was done a couple years ago, and basically everyone's proprietary implementation was a lot better, so I don't think anyone actually used it. The second version of the standard was done this summer, and it actually has, it makes networks usable with multiple instances and interconnecting rings and things like that. So there's the ITU reference if you're interested in more about it. Okay, carrier Ethernet. How are we doing on time? Okay, we're doing well. So carrier Ethernet has gotten a lot of interest in the recent couple of years, I'd say. Number one, from just a transport technology, and then we saw these carrier Ethernet exchanges coming online where they're actually trying to exchange circuits over a switch. And we have this organization called the Metronet Ethernet Forum, which defines the services and attributes that carrier Ethernet has that differentiates it from a traditional, say, LAN Ethernet. So there's a couple things: standardized services, scalability, obviously you want to sell services in different increments, reliability, quality of service, and then service management is really a big piece, and I have a whole section on the OAM mechanisms because it's so critical for carriers to provide that TDM or SONET-like OAM that they're used to. So the MEF defines several services, and as I said before, a lot of the service providers are actually involved in these service definitions, and then you can become certified. So it's good because carrier Ethernet is sort of a vague term, just like cloud computing is, and it means a lot of things to different people. So the MEF can actually certify equipment, and the MEF will also certify a network. So you can buy certified equipment, go to a certified network, and then you know what you're getting. So customers always get the same thing. The basic unit is called an Ethernet virtual connection, which is just a point-to-point VC, basically. And we can do a couple different things. We can do the E-line, which is just point-to-point. ELAN is multi-point. And then E-tree is a rooted multi-point, where the root can talk to all the nodes. Nodes can talk to the root, but they can't talk to each other. And here's some more slides that we'll skip that go into more detail about how that works. So we're going to skip all this stuff and go straight to the summary in interest of time. Here's basically the carrier Ethernet technology that we see on the market today. We have MPLS, MPLS-TP, PBB, and PBB-TE. MPLS is a very well-established technology. I started doing MPLS interop tests, I think, back in 2000. And there were deployments even before that. So it's really the Swiss Army knife of providing services. You can provide IP, L2, L3 VPN services. The standards are mature, and there's a lot of development going on. MPLS-TP is a carrier Ethernet service that's really focused on transport-level MPLS. So it's really designed to do sort of just circuit-level MPLS, and it's a work in progress in the IETF. It's getting a lot of interest by carriers, especially for mobile backhaul applications, for example, where they need circuit-like emulation over Ethernet, but they don't actually need all the complexity that IP brings. So it's really just MPLS for circuits. And I think it's definitely a market trend. PBB and PBB-TE, on the other hand, are really just designed to do carrier Ethernet services over Ethernet. They don't have the multi-service capability that MPLS brings, and that's really why, from our perspective, we see limited deployment and just not really a market trend, and there's no future development either. So if someone asked me, I want to do carrier Ethernet, what should I use? I would definitely say you want to look at MPLS because that's the mature standard. It's very widely implemented, and like I said before, there's a lot going on with MPLS. So PBB-TE, I think BT was really interested in doing that with their 21CN network a couple years ago, and then turned out to be not such a good idea, so I guess people kind of stopped talking about it. There's a bunch of references. So let's talk about OAM. So OAM is really being driven by the carrier Ethernet services, and we finally have, after many, many years, a complete protocol stack of OAM capabilities from layer 2 up to MPLS, IP, and even the VPN layer. I remember when we were first doing MPLS interop tests back in 2001, I guess, we all came together with our gear and we sat there and we plugged it in, and the LSP came up for a few minutes or a few hours, and we watched the blinking lights. We had no idea of telling if there was actually traffic going over the LSP. So now we finally have mechanisms that can do that are standards based, and like I said before, this is really trying to emulate some of the TDM and SONIC capabilities that the carriers are used to and that they want for their carrier Ethernet services. Here's basically how it works. We have a couple different services. If you look at a network, couple things going on. The first is that we have .3AH, which is a link level OAM. So this is designed just to troubleshoot and diagnose problems on a particular link. Then we move up the stack, and then we have service OAM. So there's two standards for this. There's 802.1AG and then ITU Y1713. These provide end-to-end service OAM, so you can do things like trace routes and pings. And the other thing is that the packets also take the OAM packets take the same paths that customer data takes, so it's not anything out of band. It's actually an in-band mechanism to do OAM and troubleshooting. And then in the core, of course, we have IP and MPLS OAM. We're going to skip through these because we kind of talked about them. The thing I want to point out about 1731 is that the functionality is very similar to 802.1AG, and in some senses it's a competing standard. The thing that 1731 adds on top of that is measurement. So you can actually do SLAs now, and you can actually do end-to-end latency testing to see exactly what your customers are seeing. And in fact, it supports hardware timestamps. So if your routing equipment supports that, you can actually get down to millisecond granularity on round trips and delay. So that's really important for SLA monitoring and also verification. Okay, talk about data center bridging. So we talked about this already a lot in the panel yesterday when we debated trill versus shortest path bridging. So I'll just kind of summarize, but basically the driver for this is convergence of SAN and LAN fabrics. And there are a couple things that you have to do to make SAN storage traffic actually go over Ethernet and be happy. So there's two things, and Donald said the same thing yesterday. There's really two things. There's data center bridging and then shortest path forwarding, which are going to be combined technologies that we'll use for a data center fabric. This is what people would like to do, is a converged network adapter which supports both Ethernet and fiber channel over Ethernet could be used in a data center to send both fiber channel traffic and IP traffic. The basic idea of data center Ethernet is that we have to change it to make it carry fiber channel traffic. And fiber channel traffic has a couple characteristics. Number one, it's very finicky and sensitive to latency and loss. So I was just talking about the ring protection protocol, which has 50 milliseconds failover. Well, fiber channel people kind of laugh at that because they need about 1 or 2 millisecond latency and failover, and it just can't tolerate any packet loss. For Ethernet, we have TCP and IP, which we put on top of that. So people were asking me, well, does that mean that we have lossy Ethernet today? Well, no, it doesn't. I mean, if you put a packet on the wire, if the hardware is working correctly, it'll come out on the other end correctly. What we're saying is that fiber channel doesn't have any retransmission mechanisms, so from its perspective, Ethernet needs to be lossless. What fiber channel does when the switch comes on the network is that it negotiates with all the other switches on the network, and then they actually reserve buffers and credits so that they know exactly how much data they can send through the network at one time. We just don't have that with TCP or IP, so we're really trying to make Ethernet carry fiber channel traffic. And that's the general idea here. There's 3 new enhancements which we'll talk about in the next couple slides, which were also mentioned yesterday. The first is priority flow control. This is important because right now if you have an Ethernet pause frame, it basically stops all traffic on the wire. So what Fiber Channel needs is actually a priority. So PFC introduces a per queue flow control mechanism. So you can have traffic flowing in, say, your highest priority queues, and you can put a pause frame on the wire for the lower priority queues, and that would allow the Fiber Channel traffic to continue to go in case of congestion. The other thing that's important is enhanced transmission selection, which I think is a terrible acronym, but this is basically the ability to group traffic together into a higher priority group and a certain bandwidth. So like I said before, when Fiber Channel switches come on the network, they negotiate credits and buffers and things like that. This is kind of trying to emulate that mechanism so that Fiber Channel traffic knows exactly how much it can send and receive without losing or overrunning any buffers. And the last one is called congestion notification. This works together with priority flow control when there's congestion, so it basically would put a pause frame on the wire for that queue, and then it sends a congestion notification to the ingress. The ingress gets it and says, okay, we're going to rate limit that flow, and then when the congestion period is over, then it goes full throttle again. Yeah, there's a bunch of references there that you can read about. And then the last thing we want to talk about is shortest path forwarding. There's really, I think, a great panel and a great set of tutorials that have already covered most of this, so we'll just kind of be brief. But basically, this is the network today with spanning tree, and you notice that there's a lot of red, and we don't really like that because it's really inefficient. You can do things with multiple spanning trees to load balance traffic, but it's really just difficult to do that, and I don't think anyone likes that. And the other thing too is that there's no hop count. So with wire speed forwarding, when there's a loop in your network, it's going to forward really fast. The other thing too is that during convergence, there could be periods of flooding. And when we have storage traffic on the network, that's really a bad idea. So flooding storage traffic, not a good thing, and the storage people get really unhappy when we talk about that. This is what we really want to do. So we want to have a layer 2 multipath network that has load sharing and also faster responses to failures. So with spanning tree, you have to go through this whole thing when the network recomputes. We don't really like that. Obviously, this gives us a lot of improvements in utilization and bandwidth efficiency. And the good thing is that it's actually backwards compatible with existing infrastructure. You could have a Trill cloud that is connected to a spanning tree cloud, and everything would be happy. There's 2 standards. There's Trill and shortest path bridging, which we both talked about in detail. Oh, I want to show this picture. There's Radia Perlman doing something very interesting. And then we fast forward to the summary. This is the last slide I want to talk about. If you look at from a technology perspective, Trill is really being developed for the data center right now. I think we'll see it move into other areas of the network after the standard is done, but right now it's really developed as a data center fabric application. Shortest path bridging has data center applications, but it's also designed, since it works on PBB, it's also designed for layer 2 VPN and carrier Ethernet services. The data plane is a little bit different. Trill actually has a Trill packet that it uses to encapsulate layer 2 frames, and then the MAC address is changed on each hop, just like a layer 2 or layer 3 IP packet is routed right now. The data plane for shortest path bridging, on the other hand, is encapsulation of the original frame into a backbone Ethernet frame. So it doesn't actually touch the frame as it goes to the network, whereas Trill decrements the hop count and other things as the frame goes to the network. The control plane, they're both based on ISIS. They have both have loop mitigation. Trill has the hop count, and shortest path bridging does an RPF check. They both do ECMP, multicast. You can use them with data center Ethernet. And then really, I don't think that we see shortest path bridging as a trend. Huawei and Alcatel-Lucent have basically been the only companies that I've seen talk about shortest path bridging, and I think that's more for a Metro Ethernet or layer 2 carrier Ethernet service application. Those 2 companies aren't really strong players in the data center. So I think just from a market perspective, there's a lot more people behind Trill in the data center than there are for shortest path bridging. And I think we'll see definitely Trill implementations. As Donald mentioned yesterday, there's already a interoperability event that happened in August at UNH, so that's good. I think we'll see the standard by the end of the year. Standard for shortest path bridging, they just went through draft 3.0 in June, so it's making progress, but I think the final standard is going to be middle to late next year, and then we'll see implementations after that. Here's references, and that was it. So that was 59 slides. I'm going to need a nap after this.
You can breathe. We have time for some questions.
Hi, Greg.
Hey, Ted.
Hey, who out there's pushing PBBTE now? Anybody?
I don't know of anyone that's pushing it. Just from our perspective, we don't have any customers asking us for PBBTE, and I don't think we're going to implement it.
Okay, I'm just curious. Thanks.
Yeah. We do have some customers asking us for PBB, but no one wants. The thing about PBBTE that I kind of skipped over is that all the provisioning is manual, and so I think that adds a lot of complexity because you have to have each switch along the way has to be provisioned by the by the management agent. So I think OpenFlow is kind of interesting because it almost has the same kind of concept where it wants to provision each flow along the hop. So there could be some interesting applications, but I don't have anyone that's asking us for it in particular.
Cool. Thank you.
Any more questions? Well, let's thank Greg again.